Welcome to our channel. We are so glad you found your way here. Let us help you fall asleep. Let's begin with Deep Earth Aquifers, the massive oceans hidden inside the crust. Take a slow, deep breath in and release it. Let the weight of the day fade away as we embark on an unhurried, atmospheric journey through the wonders of the cosmos. Your mind is quiet, the universe is vast, and we are ready to explore. These subsurface water reserves represent a significant yet largely unexplored frontier within planetary science. Beneath our feet lies a world where immense volumes of water exist, trapped within the porous rocks and sediments that comprise the Earth's crust. This region houses aquifers that can extend for thousands of kilometers, with water stored in complex networks of fractures and voids, showcasing a unique geological phenomenon. Through advanced imaging techniques, scientists are beginning to unravel the intricate structures that define these hidden reservoirs. The water contained within them is not merely a remnant of ancient oceans, but a dynamic component of the Earth's hydrological cycle. It serves as a crucial element in understanding the interaction between surface and subsurface environments. The composition of this water varies, influenced by the surrounding geology and the chemical processes occurring in these depths. Some aquifers may contain saline or mineral-rich water, while others harbor fresh water capable of supporting ecosystems far removed from sunlight. Pressure and temperature conditions in these depths create unique environments, enabling the study of extremophiles, organisms adapted to thrive in harsh conditions. Insights gained from these aquifers extend beyond academic curiosity. They hold implications for water resource management and environmental sustainability, shaping future exploration and conservation efforts in the face of changing climate conditions. The intricate layers of Earth reveal a complex structure, each with distinctive properties and characteristics. The crust, where surface life flourishes, serves as the outermost layer, providing a thin veneer over the planet's more substantial components. Beneath this crust lies the mantle, a semi-solid layer composed of silicate minerals that undergoes gradual convection, affecting tectonic activity and the movement of plates. These tectonic plates drift slowly, sometimes converging or diverging, which can lead to the formation of geological features like mountains, valleys, and oceanic trenches. The interactions between these plates significantly influence the localization of aquifers, creating pockets of water deep beneath the surface. As one descends further, the outer core, composed primarily of liquid iron and nickel, generates Earth's magnetic field through its dynamic movements. Below this, the inner core presents an entirely different reality, a solid sphere of iron and nickel that endures extreme conditions of pressure and temperature. Each layer possesses unique attributes, contributing to the overall behavior of the planet. The geological context in which these aquifers exist is critical, as it dictates not only the presence of water, but also the potential for life within. Understanding these relationships enhances the comprehension of subsurface environments and informs strategies for sustainable management of vital water resources. Aquifers represent geological formations capable of storing and transmitting significant amounts of water. These structures, often composed of porous rock or sediment, serve as natural reservoirs, enabling the flow and accumulation of groundwater. The characteristics of aquifers vary widely based on their composition, permeability, and the pressures exerted by surrounding materials. Porosity refers to the volume of void spaces within the material, which influences how much water can be stored. In contrast, permeability defines the ability of these formations to allow water to flow through them. This relationship is critical, as it determines the rate at which water can be extracted or replenished. The presence of confining layers, such as clay or dense rock, can impede water movement, creating confined aquifers that maintain internal pressure. Aquifers can be classified into two main types: unconfined and confined. Unconfined aquifers are directly recharged by surface water and experience fluctuations based on precipitation levels. Confined aquifers, on the other hand, are isolated from surface influences and are typically under pressure, which can lead to artesian wells when tapped. These systems play a vital role in the hydrological cycle, acting as buffers during periods of drought and supporting ecosystems dependent on subsurface water sources. Their management is crucial, as over-extraction can lead to depletion and long-term ecological consequences. The formation of deep earth aquifers occurs through intricate geological processes spanning millions of years. Groundwater flows through porous rock layers, accumulating in vast reservoirs beneath the Earth's surface. This accumulation is influenced by factors such as pressure, temperature, and the mineral composition of surrounding rocks. Over time, sedimentary layers compress, creating impermeable barriers that trap water in the underlying strata. The interplay of tectonic activity further shapes these aquifers. As plates shift and collide, fractures and faults are created, allowing water to seep into previously unreachable depths. These processes contribute to the complex architecture of the aquifer system, resulting in varying depths and water quality. In certain regions, volcanic activity introduces mineral-rich waters, enriching the aquifer and impacting its overall chemistry. Climate also plays a vital role in the formation and sustainability of these resources. Precipitation patterns dictate how quickly water is replenished, while periods of drought can lead to significant declines in aquifer levels. The interconnectedness of surface and groundwater systems ensures that changes in one can ripple through the other, influencing ecosystems and human settlements alike. Understanding these geological processes is essential for effective resource management and sustaining the delicate balance of the ecosystems reliant on these hidden reservoirs. The complexities of deep earth aquifers highlight the need for ongoing research and stewardship. Plate tectonics plays a crucial role in the formation and sustainability of deep earth aquifers. The movement of tectonic plates creates fractures and faults within the crust, providing pathways for water to infiltrate and accumulate. These geological processes enable the interaction between surface water and deeper reservoirs, facilitating the recharge of aquifers over time. Regions where plates converge often experience significant geological activity, resulting in the creation of porous rock formations. Such formations can serve as effective aquifers, allowing stored water to be accessed through natural springs or human-made wells. The nature of the rocks, including their permeability and porosity, directly influences the capacity of these aquifers to hold water. In areas where plates diverge, the resulting rift valleys and fissures can also enhance aquifer formation. Here, magma pushes up through the crust, cooling and creating new rock layers that may be more conducive to water storage. This dynamic environment leads to the continuous reshaping of aquifers, impacting their size and abundance. Thermal activity associated with tectonic processes can further influence the water chemistry within these reservoirs. Elevated temperatures can facilitate the dissolution of minerals, enriching the water with various elements. This interaction underscores the intricate relationship between tectonics and the evolution of deep earth aquifers, highlighting their vital role within the broader hydrological cycle. Non-confined aquifers surface directly into the atmosphere, allowing for easy recharge and interaction with the environment. rainwater seeps down through permeable materials, replenishing these underground reservoirs. This region is characterized by a water table that fluctuates with precipitation patterns, reflecting seasonal changes. Water levels may rise after heavy rains and recede during dry spells, creating a dynamic balance between hydrology and climate. Contrastingly, confined aquifers lie beneath impermeable layers, restricting direct interaction with the surface. These layers can consist of clay or dense rock, creating a barrier that isolates the water within. Pressure builds as water is trapped, leading to a phenomenon known as artesian flow. When tapped, these aquifers can yield water that rises spontaneously, highlighting the internal forces at play. The geology of confined aquifers often leads to more stable water supplies, insulated from surface contaminations. Both types function within the hydrological cycle, supporting ecosystems and human needs. The unconfined variety tends to be more vulnerable to surface pollutants, while confined aquifers can serve as reservoirs of ancient water sealed off for millennia. Each aquifer type plays a distinct role in maintaining regional water balance, with their unique characteristics influencing both environmental and anthropogenic systems. Understanding these differences is crucial for sustainable water management. The hydrological cycle is a complex system that encompasses both surface water and subsurface water, each playing distinct roles in the movement and distribution of water across the planet. Surface water, found in rivers, lakes, and oceans, is readily accessible and visible, serving as a lifeline for countless ecosystems and human communities. It evaporates into the atmosphere, condensing to form clouds, and eventually precipitates back to the surface, continuing the cycle. Subsurface water, residing within aquifers, remains hidden beneath layers of soil and rock. This water is often replenished by surface water through infiltration, a process that occurs slowly over time. Understanding the relationship between these two water sources is vital, as it influences the availability of fresh water for consumption, agriculture, and industry. The interaction between surface and subsurface water is complex, driven by various geological and climatic factors. In regions where aquifers are deeply buried, the connection can be tenuous, leading to significant differences in water availability and quality. Both types of water contribute to the overall health of ecosystems. Plant life relies on surface water for immediate hydration, while deeper roots often tap into the more stable subsurface reservoirs. The balance maintained within this cycle is essential for sustaining life on Earth, highlighting the intricate nature of our planet's water resources. Porosity and permeability play critical roles in the behavior of deep earth aquifers. Porosity refers to the volume of void spaces within a rock or sediment, determining how much water can be stored. This characteristic varies significantly across different geological formations. Sandy soils exhibit high porosity due to their larger particle sizes, allowing for considerable water retention. Conversely, clay-rich formations, while possessing high porosity, may hinder water movement due to their compact structure. Permeability, on the other hand, describes the ability of water to flow through these materials. Aquifers with high permeability facilitate rapid movement of water, enhancing their role in groundwater recharge and discharge. The complex interplay between porosity and permeability dictates not only how water is stored, but also how it migrates through subsurface environment. In regions where aquifers are highly permeable, water can travel considerable distances, affecting surface water bodies and contributing to broader hydrological cycles. The ability of these underground reservoirs to connect with surface ecosystems demonstrates their importance in maintaining ecological balance. Understanding the dynamics of porosity and permeability is vital for managing water resources, particularly in an era of increasing demand and climate change pressures. These geological features serve as the foundation for sustainable water management practices, ensuring long-term availability of this essential resource. Sedimentary basins play a crucial role in the formation and storage of deep earth aquifers. These expansive regions, typically characterized by layers of sedimentary rocks, provide the ideal conditions for the accumulation of groundwater. Over millions of years, the compaction of sediments creates porous spaces, allowing water to infiltrate and remain trapped within these layers. In these environments, fine-grained materials such as clay and silt contribute to the sealing of aquifers, preventing the escape of water. This containment is vital for maintaining the pressure necessary for the aquifer's functionality. The interplay between permeable and impermeable layers results in a complex system that can store vast quantities of water, often hidden beneath the Earth's surface. The geological history of sedimentary basins reveals a timeline of deposition and erosion, with ancient seas and rivers shaping their current configurations. These processes have created a network of aquifers that vary greatly in size and depth. Some extend over large geographical areas, while others are localized but still significant. The understanding of these basins is essential for assessing water resources, especially in arid regions where surface water is scarce. Research into the characteristics of these sedimentary formations continues to illuminate the intricate relationships between geology, water storage, and sustainable management practices for future generations. The mineral composition of deep aquifers significantly influences water quality, shaping not only the physical attributes of the water, but also its chemical interactions. Various minerals, such as calcite, quartz, and clay, interact with water, altering its mineral content and overall purity. These interactions occur over extensive periods, allowing for the gradual dissolution and precipitation of minerals, which in turn affects the natural filtration processes. In this context, the presence of certain minerals can indicate the potential for beneficial or harmful contaminants. For instance, elevated levels of arsenic or fluoride may arise from specific geological formations, necessitating careful monitoring and management. The interplay between the mineral composition and the surrounding geology creates a unique environment where trace elements and nutrients may either enhance or compromise water quality. Understanding these relationships is crucial for assessing the safety of water supplies sourced from deep aquifers. Regions with rich mineral content may offer waters abundant in essential minerals. Conversely, others may present challenges that require advanced filtration techniques. This complexity underscores the importance of targeted geological studies and comprehensive water quality assessments. Informed management strategies rooted in geological understanding can ensure the sustainability of these vital water resources for communities reliant on deep aquifers. The scale of deep earth aquifers reveals a vast network beneath the surface, with significant implications for water availability. These reservoirs, often located several kilometers below the Earth's crust, span across continents, hidden from immediate view. Their global distribution is not uniform. Rather, it reflects geological formations shaped over millennia. Regions rich in sedimentary rock, such as parts of North America and the Middle East, tend to harbor extensive deep aquifer systems. Hydrological studies indicate that these systems can store enormous volumes of water, with estimates suggesting they contain more fresh water than all the surface lakes combined. The interplay between porous rock layers and impermeable barriers facilitates the slow movement of water through this subsurface realm. Recharge rates vary significantly, influenced by climatic conditions and geological structures. In some areas, water can remain isolated for thousands to millions of years, a phenomenon that has led to concerns regarding its extraction and sustainability. These aquifers often serve as critical water sources for arid regions, where surface water is scarce. Their hidden presence underscores the importance of recognizing the interconnectedness of geological formations and hydrological cycles. Understanding the global distribution of deep aquifers enables more effective strategies for conservation and management, ensuring that this essential resource remains accessible for future generations. The low concept of fossil water reveals a complex history embedded within ancient aquifers. These reservoirs, formed over millennia, contain water that has remained trapped beneath the Earth's surface for thousands to millions of years. The origins of this water trace back to periods of significant climatic changes, where precipitation was abundant, allowing vast amounts to seep into the ground. Over time, geological formations sealed these water bodies, preserving them from contemporary hydrological cycles. In some regions, these ancient aquifers are remnants of prehistoric lakes and rivers, their existence a testament to Earth's dynamic climate history. The slow movement of water through porous rock and sediment contributes to the gradual accumulation of this resource, creating a delicate balance between replenishment and depletion. It is essential to recognize that extraction from these aquifers often exceeds natural recharge rates, raising concerns about sustainability. The chemistry of fossil water can also provide insights into past climates and environmental conditions. Isotopic analysis reveals distinct signatures, allowing scientists to reconstruct historical weather patterns and assess long-term changes in ecosystems. The study of these ancient waters not only enhances understanding of Earth's geological processes, but also highlights the importance of judicious management practices. In this way, the legacy of fossil water remains intricately linked to both the present and the future. Geophysical techniques play a crucial role in detecting deep aquifers, revealing the hidden reservoirs beneath the Earth's surface. These methods utilize variations in physical properties to infer the presence of water. Seismic surveys, for instance, measure the speed at which seismic waves travel through the ground. Changes in wave velocity can indicate the existence of saturated rocks, suggesting aquifer locations. Electrical resistivity methods also provide insights, exploiting the difference in conductivity between water-saturated materials and dry rocks. By injecting an electrical current into the ground and measuring the response, it becomes possible to delineate aquifer boundaries and assess their depth. Ground-penetrating radar, utilizing electromagnetic waves, offers a non-invasive approach to visualize subsurface structures. Variations in dielectric properties allow for the identification of water-saturated zones. Magnetotellurics, which analyze natural electromagnetic fields, further assist in mapping deep aquifers. This technique can detect water-bearing formations at significant depths, often exceeding several kilometers. Satellite remote sensing contributes to this endeavor, using surface characteristics to infer subsurface water presence, although its resolution is limited compared to ground-based methods. Each technique provides unique advantages, enabling scientists to create comprehensive models of deep aquifers. Collectively, these methods enhance understanding, offering insights into the vast, concealed water resources that sustain ecosystems and human activity. Seismology plays a critical role in identifying and mapping the locations of deep earth aquifers. This discipline utilizes seismic waves generated by earthquakes or artificial sources to probe the subsurface layers. As these waves travel through different geological formations, they provide vital data regarding the composition and structure of the crust. Variations in wave speed and behavior reveal the presence of water-saturated zones, allowing researchers to infer the locations of potential aquifers. In this process, the Earth's crust behaves like a complex medium, with seismic waves responding to the unique characteristics of each layer. The detection of anomalies in wave propagation can indicate the presence of larger voids filled with water. These findings are further validated through complementary techniques such as electromagnetic surveys and geological mapping, which enhance the understanding of the hydrological systems at play. The information gathered not only aids in locating aquifers, but also contributes to assessing their capacity and sustainability. This knowledge is essential for managing water resources, particularly in regions facing scarcity or contamination. Understanding the interconnectedness of these aquifers with surrounding geological features is crucial for both ecological preservation and the provision of clean water for human consumption. Insights gained from seismological studies continue to shape the approach to water management in an increasingly resource-constrained world. Ground-penetrating radar serves as an essential tool for exploring subsurface water sources, offering a non-invasive method to investigate the complexities of these hidden reserves. This technology utilizes electromagnetic radiation to detect and delineate various subsurface materials, providing a clearer understanding of geological formations. The precision of ground-penetrating radar allows researchers to identify the boundaries of aquifers and assess their extent, facilitating more informed decision-making regarding water resource management. Analyzing the signals reflected back from different layers reveals valuable information about water saturation levels and the physical properties of surrounding materials. This method enhances the ability to map the intricate web of aquifers beneath the Earth's surface, revealing their interactions with soil and rock formations. With the increasing demand for fresh water, the importance of accurately locating and managing these reserves becomes ever more critical. In regions where traditional drilling methods may pose risks to the environment or yield insufficient data, ground-penetrating radar emerges as a sustainable alternative by minimizing the ecological footprint while maximizing information retrieval. It assists in the effective planning and utilization of water resources. Continuous advancements in radar technology promise even greater resolution and depth of analysis, ensuring these hidden oceans within the crust are explored with increasing efficiency and accuracy. The implications for sustainable water management remain profound, influencing future strategies in resource preservation. Water storage capacity within deep earth aquifers is vast, often exceeding that of surface reservoirs. These subterranean bodies of water can hold approximately 2 million cubic kilometers of liquid, representing a significant portion of the planet's freshwater resources. This region, nestled beneath layers of rock and sediment, acts as a natural reservoir, its water slowly seeping through porous materials over millennia. The intricate geology shapes these aquifers, with permeable rock formations facilitating the movement and accumulation of water. The combination of pressure and temperature at these depths ensures that the water remains in a liquid state, even under extreme conditions. Such environments foster unique ecosystems where microbial life thrives in isolation, revealing clues about life's resilience. The rates at which this water can be replenished vary considerably, often dictated by the surrounding geological formations and climatic conditions above. Recharge processes can take thousands of years, making it critical to manage these resources wisely. Extraction for human use must be balanced with conservation efforts to sustain these hidden reservoirs for future generations. This region's role in the hydrological cycle is pivotal, influencing not only local ecosystems but also global patterns of water distribution. Understanding the complex dynamics of deep earth aquifers is essential for effective environmental stewardship. Groundwater recharge plays a critical role in sustaining deep earth aquifers, influencing both water quality and availability. This process occurs when precipitation infiltrates the surface, moving through soil and rock layers to replenish underground reservoirs. In many regions, the rate of recharge is heavily dependent on geological formations, soil types, and climate conditions. Areas with permeable rock structures allow for more efficient movement of water, while those with compacted layers can impede this natural flow. Ardoritose and permeable rock structures allow for more efficient movement of water. They not only store resources, but also act as natural filters, cleansing impurities from the infiltrating water. This filtration process is vital for maintaining the health of ecosystems dependent on groundwater. Fluctuations in recharge rates Vanligt the så Ellingskorsa vidast spagli för penningspunds dependent on groundwater. Fluctuations in recharge rates, driven by seasonal variations or human activity, can disrupt this balance, leading to either over-extraction or contamination. The relationship between aquifers and groundwater recharge is further complicated by land use practices. Urbanization often creates impermeable surfaces, preventing water from seeping into the ground. Agricultural practices that deplete soil moisture can also diminish recharge rates, exacerbating water scarcity in vulnerable regions. Monitoring these interactions is crucial for ensuring the sustainability of both aquifers and the ecosystems that rely on them. Continued research into these dynamics will enhance understanding of their interconnectedness within the broader hydrological cycle. Temperature gradients within deep aquifers reveal critical insights into their thermal properties. These gradients often exhibit significant variations influenced by factors such as geological composition and proximity to tectonic activity. In many regions, temperature increases at a consistent rate of approximately 30 degrees Celsius for every kilometer of depth. This phenomenon, known as the geothermal gradient, serves as a key indicator of subsurface conditions. The thermal behavior of these aquifers can affect not only water quality, but also the movement of fluids within the Earth's crust. As depth increases, pressure rises, altering the physical and chemical characteristics of the aquifer water. Elevated temperatures can enhance the solubility of minerals, leading to diverse geochemical interactions. Such processes create complex environments where dissolved constituents may vary significantly from surface waters. Thermal properties also play a role in the extraction of geothermal energy. Regions with high temperature gradients present opportunities for harnessing heat as a sustainable resource. This energy can contribute to the generation of electricity or provide direct heating options for residential and industrial applications. Understanding these temperature dynamics is essential, as it informs not only resource management, but also the potential impacts of climate change on freshwater availability. The interplay between heat and water in these depths continues to be a vital area of exploration within earth sciences. This region's deep aquifer systems are increasingly vulnerable to the effects of climate change. Elevated temperatures influence the pressure and thermal gradients within these subterranean reservoirs, potentially altering the delicate balance that sustains them. As surface conditions shift, the hydrological cycle undergoes disruption, leading to changes in precipitation patterns. These variations can result in reduced recharge rates, threatening the stability of these vast underground water sources. Sea level rise introduces additional complexities. Coastal aquifers face saltwater intrusion, further compromising the freshwater resources held within. The encroachment of saline water not only impacts the quality of the aquifer, but also poses risks to ecosystems and agricultural practices that depend on clean water. In regions where these deep systems are already stressed, reliance on surface water becomes untenable, heightening the stakes for both human and ecological communities. Monitoring efforts are crucial as scientists seek to understand the intricate connections between climate dynamics and aquifer health. Data collection facilitates the prediction of potential shifts in water availability, allowing for adaptive management strategies. These insights inform water conservation policies and sustainable practices, striving to mitigate the impacts of climate change on these essential resources. The sustainable management of aquifers remains imperative for securing water supplies amid an uncertain future. The interaction between surface water bodies and deep aquifers presents a complex relationship that significantly influences both ecosystems and water resources. Surface water often seeps into the ground, replenishing these hidden reservoirs. This process, known as groundwater recharge, occurs primarily in areas where the soil composition allows for efficient infiltration. The connection is particularly evident in regions where rivers, lakes, and wetlands exist in proximity to aquifers. As water percolates through layers of soil and rock, it undergoes natural filtration, enriching the aquifer with essential minerals while simultaneously maintaining the balance of local hydrological cycles. Groundwater, in turn, can discharge into surface water bodies, sustaining flows during dry periods. Such exchanges help maintain the health of aquatic ecosystems, providing critical habitats for various species. Contaminants from surface activities can threaten this delicate equilibrium. Agricultural runoff, industrial discharge, and urban development introduce risks to both the quality and quantity of water within aquifers. Monitoring these interactions is crucial for effective water management strategies. Understanding the dynamics between surface and subsurface environments aids in predicting how changes in one system may impact the other, particularly as climate change intensifies variability in precipitation and evaporation patterns. The resilience of both groundwater and surface water systems relies on their interconnectedness, forming the backbone of many regional water supplies. Deep aquifers serve as critical reservoirs, providing a substantial volume of water that supports ecosystems and human activities alike. These subterranean formations, often located beneath layers of impermeable rock, act as a buffer during periods of drought, moderating the fluctuations in surface water availability. This region holds vast quantities of water, which gradually infiltrates through geological formations, replenishing the aquifers over time. The interaction between deep aquifers and surface water bodies contributes significantly to regional hydrology. As water seeps from aquifers, it often emerges in springs, feeding rivers and lakes, thereby sustaining flora and fauna dependent on these ecosystems. Groundwater extraction for agricultural and urban uses draws from these depths, highlighting their importance in maintaining water security. In many areas, the stability of local climates is directly linked to the health of these hidden reservoirs. Over-extraction, however, can lead to subsidence and diminished water quality, posing challenges for sustainable management. Monitoring these aquifers becomes essential as they not only store water but also influence regional geological stability. Understanding the dynamics of deep aquifers reveals the complex interdependencies within hydrological cycles. The intricate balance they maintain underscores the necessity of preserving this vital resource, ensuring that future generations can rely on their benefits. Groundwater movement within aquifers occurs through a complex interplay of geological formations and hydrological processes. The porous nature of these underground structures facilitates the flow of water, which can traverse vast distances over extended periods. This movement is primarily driven by gravitational forces, creating a gradient that encourages water to migrate from areas of higher pressure to lower pressure. Factors such as soil composition, permeability, and the presence of confining layers significantly influence flow dynamics. In regions where sediment is highly permeable, water can move rapidly, while in areas with dense rock formations, flow may be considerably slower. Understanding these variations is crucial for effective water management, particularly in regions relying heavily on aquifers for agricultural and domestic purposes. Recharge processes also play a vital role in sustaining aquifer levels. Precipitation infiltrates the soil, replenishing these reserves. Though the rate of recharge can be affected by land use and climate conditions, seasonal variations can lead to fluctuations in groundwater levels, revealing the delicate equilibrium maintained within these systems. As extraction increases, the implications for both groundwater availability and surface ecosystems become more pronounced. Monitoring and managing these underground resources is essential to ensure the longevity of aquifers and the myriad of life forms that depend on them. The intricate processes governing their dynamics remain a focal point for researchers and conservationists alike. Like Waditio, sustainable aquifer management is essential for maintaining the delicate balance of these hidden reservoirs. Their ability to store vast quantities of fresh water plays a crucial role in supporting ecosystems and human populations alike. Proper stewardship involves understanding the recharge rates and the interconnectivity with surface water bodies. Excessive extraction can lead to significant declines in water levels, resulting in detrimental effects on both the environment and communities relying on these resources. Conservation efforts emphasize the importance of protecting the surrounding landscapes that contribute to aquifer replenishment. Vegetation plays a vital role in maintaining soil integrity and facilitating the infiltration of rainwater. These regions are often sensitive to land use changes, which can disrupt natural hydrological cycles. Implementing strategies to minimize contamination and promote sustainable agricultural practices aids in preserving water quality. Research continues to unveil the complexities of aquifers, revealing their response to climate variability and human activities. This understanding is fundamental in formulating policies aimed at safeguarding these vital resources. The integration of advanced technologies, including remote sensing and modeling, offers innovative solutions for monitoring and managing aquifer health. Over-extraction poses a significant threat to these deep aquifers, as human demand for fresh water continues to rise. The process often involves drilling deep into the Earth's crust, tapping into reservoirs that have remained untouched for millennia. This relentless pursuit can lead to a depletion of these vital resources, resulting in a decline in water quality and availability. Pollution compounds the challenges faced by these underground reservoirs. Contaminants from industrial activities, agricultural runoff, and urban development seep into the ground, infiltrating aquifers and disrupting their delicate ecosystems. These pollutants can render the water unsafe for consumption, impacting not only human health but also the flora and fauna that depend on these sources. The repercussions of such actions extend beyond immediate human needs. The depletion and contamination of deep aquifers can lead to geological instability, affecting land use and possibly triggering subsidence. As water levels drop, the structural integrity of surrounding environments may be compromised, altering landscapes and ecosystems. Protecting these hidden oceans requires a multifaceted approach that considers sustainable practices in water extraction and land management. Restoration efforts are critical, as is the need for greater awareness of the interconnectedness of human actions and deep geological systems. Through careful stewardship, it is possible to mitigate the adverse effects inflicted upon these ancient reservoirs. Soramiti of Prumith falls around the world reveal the incredible diversity and significance of these hidden waters. The Great Artesian Basin in Australia stands as one of the largest and most extensive aquifer systems globally, spanning over 1 million square kilometers. It provides vital water resources for agriculture and human consumption in a region characterized by arid conditions. The interconnected layers of sandstone and limestone hold vast quantities of water, accumulated over millennia. In North America, the Ogallala Aquifer serves as a crucial resource for the agricultural heartland, stretching across 8 states. It sustains crops and livestock, yet it faces significant depletion due to over-extraction. This complex aquifer system, primarily composed of porous sediments, illustrates the delicate balance between consumption and natural replenishment. Across the globe, the Nubian Sandstone Aquifer System, located beneath parts of Libya, Egypt, Sudan, and Chad, highlights the geopolitical challenges associated with groundwater resources. Its vast reserves, formed over millions of years, are largely untapped, but hold potential for addressing water scarcity in a rapidly changing climate. In each case, the intricate geology and hydrology of these aquifers underscore their importance. Understanding their dynamics becomes essential for ensuring sustainable usage and protecting them from the pressures of modern society. The Great Artesian Basin serves as a prime example of deep aquifer systems, extending over 1 million square kilometers across Australia. This vast reservoir is composed of several layers of porous rock, allowing water to flow freely through its interconnected formations. Recharge occurs primarily in the northern regions, where rainfall seeps into the ground, initiating a slow journey that can span thousands of years. These waters are under considerable pressure, emerging naturally at the surface in various locations, creating springs that sustain unique ecosystems. The basin holds an estimated total of 300,000 gigaliters of water, a resource critical for agriculture, industry, and communities. It represents a delicate balance, where extraction for human use must be carefully managed to avoid depletion. The geological history is noteworthy, shaped by ancient sea levels and tectonic movements that have created a complex network of rock layers. This region showcases the interplay between geological processes and hydrology, offering insights into how deep aquifers function. The relationship between surface conditions and subterranean reservoirs is intricate, illustrating the importance of maintaining a sustainable approach to resource management. The basin's significance extends beyond its immediate utility, serving as a vital indicator of environmental health and climate variability. Reflecting changes in both local and global contexts, the Ogallala Aquifer stands as one of the largest aquifers in the world, spanning 8 states in the central United States. This immense reservoir provides water for agricultural irrigation, which supports a substantial portion of the nation's food supply. Its vastness underscores the essential role it plays in sustaining both local economies and ecosystems. The aquifer's water level has been declining steadily due to extensive withdrawal rates, raising concerns about its long-term viability. Groundwater extraction in this region occurs at a rate that often exceeds the natural recharge, creating a significant imbalance. Agricultural practices, particularly in arid and semi-arid regions, exacerbate this situation, leading to increased reliance on these subterranean resources. Over the decades, it has become increasingly evident that the Ogallala Aquifer's health directly correlates with agricultural productivity and economic stability within the region. Challenges arise not only from depletion but also from contamination risks posed by agricultural runoff and industrial activities. These factors contribute to complex dynamics that threaten the aquifer's integrity. Efforts to promote conservation and sustainable practices are critical for ensuring its longevity. The health of the Ogallala Aquifer serves as a barometer for broader environmental concerns, reflecting the interconnectedness of climate, agriculture, and water management. Continued monitoring and adaptive strategies will be essential for navigating the future of this vital resources, resulting in a decline in water quality and availability. Deep aquifers provide a consistent supply of fresh water, enabling the cultivation of crops essential to food security. Their vast reserves, often accumulated over millennia, support irrigation systems that sustain farming communities, allowing for the cultivation of staple crops such as wheat, rice, and corn. Groundwater extracted from these aquifers is often less susceptible to evaporation than surface water, making it an ideal choice for agricultural practices. In temperate zones, it facilitates year-round farming, while in drier climates, it enables the expansion of arable lands into previously inhospitable areas. The management of these underground reserves is crucial, as excessive withdrawal can lead to depletion, land subsidence, and deterioration of water quality. The interconnectedness of deep aquifers and agricultural productivity underscores their importance in addressing global food demands. As populations grow, reliance on these resources increases, necessitating sustainable practices that balance extraction with replenishment. This delicate equilibrium is vital not only for food security, but also for maintaining the overall health of ecosystems. Future agricultural strategies must incorporate advanced technologies and holistic approaches to ensure that these hidden oceans within the Earth continue to support humanity's nutritional needs. Depletion of aquifers occurs due to a combination of over-extraction, climate change, and land use alterations. Intensive agricultural practices often demand excessive water, leading to the gradual draining of these critical resources. Increasing population pressures exacerbate the situation as urban expansion consumes groundwater at an unsustainable rate. Each year, billions of liters are withdrawn, diminishing the reservoir levels beneath the surface. Consequences manifest in several forms, impacting both ecosystems and human communities. Lowering water tables can lead to land subsidence, where the ground sinks due to the loss of structural support. This phenomenon disrupts infrastructure and can permanently alter the landscape. In some regions, the reduction of aquifer levels contributes to the drying of nearby rivers and wetlands, which play essential roles in biodiversity. The diminishing aquifers also pose a threat to agricultural productivity. Crops heavily reliant on irrigation may fail under water scarcity, resulting in reduced yields and heightened food insecurity. Communities that depend on these groundwater sources for drinking water face challenges in accessing clean supplies, leading to health concerns and potential conflicts over remaining resources. Efforts to mitigate aquifer depletion are underway, emphasizing sustainable management practices. Addressing these challenges requires a careful balance between human needs and the preservation of this vital resources, ensuring its longevity for future generations. The economic value of deep earth aquifers extends beyond mere water supply. It encompasses a myriad of industries dependent on this hidden reservoir. Agriculture relies heavily on these sources for irrigation, particularly in arid regions where surface water is scarce. The ability to access fresh water from deep aquifers provides a critical safety net for food production, supporting both local economies and global markets. Mining operations also benefit significantly from the availability of groundwater, utilizing it for mineral extraction and processing. This reliance on subterranean water underscores the interdependence of various sectors, revealing how these aquifers act as a foundation for industrial growth. The extraction of geothermal energy offers another layer of economic potential, as these aquifers can facilitate sustainable energy production, reducing reliance on fossil fuels. Tourism and recreation industries find their niche in the landscapes shaped by aquifer systems, such as enchanting springs and unique geological formations. The allure of these natural wonders draws visitors, contributing to local economies and promoting environmental stewardship. The challenge lies in quantifying this value accurately. as the benefits extend into realms often overlooked. Sustainable management practices must be adopted to ensure that economic gains do not come at the expense of ecological integrity. The balance achieved will determine the future resilience of these essential deep earth resources. Interactions among geology, hydrology, and climate science reveal intricate relationships that govern the existence of deep earth aquifers. These vast reservoirs play a critical role in maintaining ecological balance, acting as both sources of freshwater and buffers against climate variability. Geological formations, shaped over millions of years, dictate the pathway through which water can flow, influencing both the size and distribution of these aquifers. Hydrological cycles, which dictate the movement of water between the surface and subsurface, rely heavily on the structural integrity of the Earth's crust. The porosity and permeability of geological materials control the rate at which water infiltrates and is stored within these hidden layers. As climate patterns shift, the availability of surface water becomes unpredictable, intensifying reliance on these subterranean stores. Changes in temperature and precipitation patterns create feedback loops that affect groundwater recharge rates. Decreased rainfall can lead to diminished aquifer levels, while increased temperatures heighten evaporation rates, further straining these vital resources. Understanding this intersection is essential for developing sustainable management strategies that ensure this precious water remains available for future generations. The interplay of geological formations, hydrological processes, and climate dynamics forms a delicate equilibrium, one that must be carefully studied and preserved to safeguard the planet's water security. The integrity of deep aquifers is frequently compromised by various contaminants, which can originate from both natural processes and human activities. These geological reservoirs, while often pristine, are not immune to the encroachment of pollutants such as heavy metals, pesticides, and industrial chemicals. The natural filtration provided by layers of rock and sediment may mitigate some risks, yet it is not a foolproof barrier. Over time, these contaminants can accumulate, posing serious risks to water quality. Monitoring and assessment of these hidden water sources are essential to identify potential threats. Advanced techniques in hydrogeology allow scientists to detect trace levels of hazardous substances, enabling early intervention. Remediation strategies are being developed to address contamination in aquifers. These may include bioremediation, which uses microorganisms to break down pollutants, or advanced filtration methods that enhance the natural cleansing capacity of aquifer systems. Public awareness and policy interventions also play vital roles in protecting these resources. Sustainable land use practices can minimize the introduction of harmful substances, while regulatory frameworks aim to limit industrial discharges and agricultural runoff. The sustainable management of deep aquifers not only preserves their water quality, but also ensures the longevity of these vital resources for future generations. Understanding the delicate balance within these systems is key to fostering a safe and sustainable water supply. Natural filtration plays a crucial role in maintaining the health of aquifer systems. Through the process of percolation, water seeps through layers of soil and rock, effectively removing contaminants and impurities. These layers act as a natural barrier, ensuring that only clean, potable water reaches the aquifers beneath. The geological composition of this region significantly influences the filtration efficiency. For instance, porous sandstone and limestone facilitate the movement of water, while clay layers can impede it, creating a complex interplay that affects overall water quality. As rainwater infiltrates the ground, it interacts with various minerals, leading to essential chemical processes. These processes not only cleanse but also enrich the water with vital nutrients. Microbial communities thrive within these aquifers, breaking down organic matter and further purifying the water supply. This intricate system of filtration underscores the importance of protecting these natural resources from pollution and over-extraction. Sustainable management practices must consider the delicate dynamics at work within these subterranean reservoirs. Groundwater recharge, the process by which surface water replenishes aquifers, is equally vital. Maintaining the balance between extraction and replenishment ensures that this hidden ocean remains a reliable source of fresh water for ecosystems and human use. The synergy between geological formations and biological processes is essential for the longevity of these vital aquifer systems. Groundwater salinization poses a significant threat to the integrity of aquifers, impacting both water quality and availability. This phenomenon occurs when saline water intrudes into freshwater resources, often accelerated by human activities such as excessive groundwater extraction and land use changes. In coastal regions, the encroachment of seawater into aquifers exacerbates this issue, leading to a gradual deterioration of freshwater supplies. The implications of salinization extend beyond mere chemical changes. They affect agricultural productivity, drinking water sources, and ecosystem health. Crops that rely on freshwater become increasingly vulnerable as soil salinity reduces their yields and resilience. The delicate balance between freshwater and saline environments is disrupted, prompting a need for effective management strategies. And mitigation efforts focus on both preventing salinization and rehabilitating affected areas. Sustainable groundwater management practices include regulated withdrawal rates to maintain pressure in aquifers, which helps to deter saline intrusion. Additionally, the implementation of recharge areas where rainwater and surface water are allowed to percolate into the ground can bolster freshwater supplies. FDF technologies such as reverse osmosis and desalination processes offer further solutions enabling the treatment of saline water for agricultural and potable uses. Continued research into these methods and their applications is crucial for preserving the health of both aquifers and the ecosystems they support. The interplay between deep aquifers and geothermal resources reveals significant insights into the Earth's subsurface dynamics. These aquifers, often situated several kilometers beneath the surface, serve as reservoirs of freshwater while simultaneously hosting heat from the planet's interior. This latent thermal energy can be harnessed for various purposes, including electricity generation and direct heating applications. Temperature gradients within these regions can reach extraordinary levels, indicating that the proximity to geothermal reservoirs enhances the thermal capacity of the surrounding aquifer. The geothermal energy arises from the decay of radioactive isotopes and residual heat from planetary formation, contributing to a complex thermal environment. This relationship can be observed in regions characterized by volcanic activity, where groundwater is heated and can exhibit boiling phenomena. Monitoring the interaction between these aquifers and geothermal systems offers crucial data that may inform sustainable resource management. Understanding fluid movement and temperature profiles within these systems allows for the optimization of geothermal energy extraction, minimizing environmental impacts. Furthermore, the potential for induced seismicity presents a challenge as pressurized fluids are injected or extracted from these deep aquifers. Balancing the extraction of geothermal energy with the preservation of aquifer integrity necessitates careful scientific investigation. The findings from this ongoing research The role of aquifers in carbon sequestration represents a critical intersection between geological processes and climate dynamics. These deep subterranean reservoirs possess the capacity to store significant amounts of carbon dioxide, effectively acting as a natural buffer against atmospheric accumulation. Situated within permeable rock formations, they provide suitable environments where carbon can react with minerals, forming stable compounds and preventing its release back into the atmosphere. Research indicates that this process occurs over geological timescales, enhancing the long-term efficacy of aquifer systems in mitigating climate change. The interaction between carbon dioxide and minerals, such as calcium and magnesium silicates, facilitates the formation of carbonate minerals. This mineralization not only sequesters carbon, but also contributes to the structural integrity of the aquifer, reinforcing its role in groundwater management. The implications of these processes extend beyond carbon capture. They influence the hydrology of surrounding regions, affecting water quality and availability. As carbon dioxide is injected into aquifers through various methods, careful monitoring ensures that the integrity of these systems is maintained, preventing contamination of groundwater supplies. In this context, understanding the intricate dynamics of deep earth aquifers becomes essential. Their potential to sequester carbon highlights their importance not only for climate stability, but also for the sustainability of water resources in an ever-changing environment. These natural systems represent a vital facet of our planet's geological and atmospheric health. Legal frameworks surrounding aquifer use ensure that these vital resources are managed sustainably. Various jurisdictions impose regulations designed to protect these hidden reservoirs, recognizing their importance to both human consumption and ecological balance. Water rights, often entangled in complex legal statutes, dictate who can access and utilize these underground supplies. Groundwater management strategies emerge from local, regional, and national policies, reflecting the unique characteristics of each aquifer. Some regions implement permitting systems that require users to obtain authorization before extracting water, thereby promoting responsible usage. This regulatory approach aims to balance consumer needs with environmental conservation, acknowledging the interconnectedness of surface and groundwater. Monitoring programs play a crucial role in compliance. They track water levels and quality, allowing authorities to identify trends and respond to potential over-extraction or contamination. Legal measures enforce penalties for violations, underscoring the commitment to preserving this essential resource for future generations. International agreements also influence aquifer management, particularly in transboundary situations where water flows across borders. Negotiations between countries foster cooperative approaches, emphasizing the shared responsibility to protect these vital ecosystems. Emerging scientific research informs these regulations, enabling policymakers to adapt to changing circumstances and evolving understanding of aquifer dynamics. The continuous dialogue between legal frameworks and scientific insight ensures the safeguarding of these critical geological features. Traditional water management practices have long recognized the significance of deep aquifers. Indigenous communities have developed intricate systems to utilize and preserve these vital resources, often drawing on generations of accumulated knowledge. This understanding encompasses seasonal cycles, local hydrology, and the intricate relationships between various ecosystems. Such practices, rooted in a profound respect for the environment, emphasize sustainability. Water sources are not merely viewed as commodities. Instead, they are treated as sacred entities that require stewardship. These communities have often thrived in regions where modern approaches to water management have struggled, demonstrating the effectiveness of their traditional methods. In many cases, the deep aquifers serve as a critical lifeline during periods of drought, providing a reliable source of fresh water. The management of these resources reflects a deep awareness of both the physical landscape and the social dynamics within communities. The structures and practices established to manage water reflect a balance between meeting immediate needs and ensuring long-term availability. Understanding this knowledge fosters a collaborative approach to modern water management, integrating scientific research with indigenous wisdom. The lessons learned from these traditional systems can enhance contemporary strategies, safeguarding deep aquifers while respecting the cultural heritage that accompanies them. The coexistence of these perspectives holds great potential for future water security and ecological resilience. The integration of advanced technology plays a crucial role in the ongoing assessment of aquifer health. Remote sensing techniques, utilizing satellites equipped with specialized sensors, offer invaluable insights into subterranean water levels and their fluctuations. This capability allows for the continuous monitoring of vast regions, providing data that is essential for understanding the dynamics of these hidden reservoirs. Ground-penetrating radar offers another layer of information, revealing the structure and composition of the aquifers beneath. Such tools can identify changes in porosity and permeability, factors that directly influence water movement and storage capacity. The application of these technologies enables scientists to create detailed models, enhancing predictions about aquifer responses to both natural and anthropogenic influences. Hydrogeological modeling further supports the understanding of groundwater flow patterns and recharge rates. By simulating various scenarios, it becomes possible to assess the impacts of climate change, land use alterations, and population growth on aquifer sustainability. These simulations provide a framework for developing effective management strategies aimed at preserving these vital resources. Data from these technologies contribute to a holistic understanding of aquifer health, guiding conservation efforts and informing policy decisions. As research continues to evolve, the synergy between technology and environmental science will be pivotal in maintaining the integrity of deep earth aquifers, ensuring their role in global water security for generations to come. Climate variability introduces significant challenges to aquifer sustainability, altering the delicate balance between recharge and extraction. Fluctuations in precipitation patterns, driven by shifting climatic conditions, directly influence the volume of water that permeates through soil layers into these subterranean reservoirs. Extended periods of drought can severely diminish the replenishment rates, leaving aquifers vulnerable to over-extraction. In areas where agricultural practices dominate, increased demand for irrigation exacerbates this strain. The consequences can manifest in declining water tables, which may lead to land subsidence and diminished water quality. The interconnectedness of surface water and groundwater systems makes these effects even more pronounced, as reduced surface flows further limit the natural recharge processes necessary for aquifer health. Conversely, sudden surges in rainfall can lead to flooding, which may initially appear beneficial but often results in runoff that bypasses aquifers entirely, failing to contribute to their replenishment. This scenario underscores the unpredictability of climate systems and the importance of adaptive management strategies. Understanding these dynamics is essential for developing sustainable practices. By monitoring changes in climate patterns and implementing conservation measures, it becomes possible to safeguard these critical resources. Continued research will clarify the intricate pathways through which climate variability impacts aquifer integrity, reinforcing the need for informed stewardship of this hidden yet vital water supply. Technological advancements in desalination present a compelling alternative to groundwater extraction. This method, which converts seawater into potable water, offers a potential solution to the growing demand for fresh water. It has gained attention in regions facing severe water scarcity, where traditional aquifers are depleted. By harnessing this technique, communities can alleviate pressure on dwindling underground reserves, allowing for their natural replenishment. The implications of widespread desalination extend beyond immediate water supply. It introduces a shift in resource management strategies, promoting a sustainable balance between surface and subterranean water resources. As these systems become more efficient and cost-effective, they may lead to a reduced dependency on aquifers, contributing to their preservation. Innovative approaches, such as integrating renewable energy sources into desalination processes, further enhance sustainability. Utilizing solar or wind power not only minimizes the carbon footprint, but also aligns with global efforts to mitigate climate change impacts. Research continues to explore the long-term effects of desalination on local ecosystems and hydrology. The introduction of large quantities of brine back into ocean systems needs careful evaluation, as it could affect salinity levels and marine life. Understanding these dynamics will be essential for developing responsible policies that protect both aquifers and surrounding environments, while ensuring water security for future generations. Innovations in aquifer recharge techniques are gaining attention as critical advancements in sustainable water management. Various methods have been developed to enhance the natural replenishment of these vital resources. One approach involves the intentional infiltration of surface water into the ground, utilizing designed basins that capture runoff during rainy seasons. This strategy allows excess water to percolate down, replenishing the underground reservoirs. Technological advancements also play a role in optimizing recharge efforts. Monitoring systems equipped with sensors provide real-time data on groundwater levels, enabling precise management of water resources. This information allows for better scheduling of recharge activities, ensuring that efforts are made during optimal conditions for maximum efficacy. Another innovation focuses on the use of permeable pavements and green infrastructure in urban environments. These techniques facilitate water absorption, reducing surface runoff while enhancing aquifer recharge. Such methods help mitigate the impacts of urbanization on natural water cycles, supporting the sustainability of local water supplies. Research is ongoing in the exploration of artificial recharge systems, which may utilize treated wastewater to replenish aquifers. This approach presents a dual benefit, addressing wastewater management while augmenting water supplies. Collectively, these innovations are shaping a future where aquifer recharge becomes a standard practice, ensuring the longevity and health of these essential underground water systems. Artificial intelligence is increasingly influencing aquifer management, providing sophisticated tools to analyze vast datasets. By integrating climatic variables, geological characteristics, and human activity patterns, these systems generate predictive models that can forecast water availability and demand. This capability allows for more informed decision-making regarding aquifer extraction and replenishment strategies. Remote sensing technologies, combined with AI algorithms, enhance monitoring efforts. They detect subtle changes in land surface and groundwater levels, offering real-time insights into the health of aquifers. Such data can identify over-extraction or contamination, enabling timely interventions to protect these vital resources. Machine learning techniques contribute to optimizing water use in agricultural practices. Adjustments to irrigation schedules and methodologies can be made based on AI recommendations, ensuring that water is utilized efficiently. This reduction in waste not only conserves aquifers but also promotes sustainable agricultural yields. AI-driven platforms facilitate collaboration among stakeholders by sharing information and insights. Local governments, farmers, and environmental organizations can coordinate efforts to maintain aquifer integrity. This collaborative approach includes the development of policies that support sustainable extraction practices. Urban development increasingly interacts with aquifer resources, often leading to complex challenges. As cities expand, the demand for freshwater rises, placing immense pressure on these hidden reservoirs. groundwater extraction intensifies, with many regions relying on these aquifers for drinking water, agriculture, and industry. The relationship between urban growth and aquifer sustainability requires careful management, as over-extraction can lead to depletion, land subsidence, and degradation of water quality. Contamination poses a significant risk, particularly from urban runoff, industrial discharges, and septic systems. Chemical pollutants can infiltrate aquifers, jeopardizing the very resources that communities depend upon. This interaction highlights the critical need for monitoring and regulation, ensuring that development does not come at the expense of water security. Technological advancements in hydrology and geophysics provide tools for better understanding aquifer dynamics. These methods allow for the assessment of groundwater levels, flow patterns, and recharge rates, facilitating informed decision-making. Integrated water resource management emerges as a vital framework, balancing the needs of urban populations with those of the aquifers beneath. In areas of rapid urbanization, public awareness and community engagement become essential components. Educating citizens about the importance of aquifers fosters a sense of stewardship, encouraging practices that protect these vital resources for future generations. Land use changes exert profound effects on aquifer systems, reshaping the delicate balance of groundwater resources. Urbanization leads to increased impermeable surfaces, restricting natural recharge processes. Rainwater, instead of seeping into the ground, often flows into storm drains, diminishing the amount that replenishes these hidden reservoirs. Agricultural practices introduce chemicals and fertilizers, which may leach into the groundwater, altering its quality and threatening ecosystems dependent on these sources. Deforestation also plays a critical role. The removal of trees disrupts the natural hydrological cycle, reducing transpiration and consequently lowering precipitation in certain areas. This results in decreased soil moisture, affecting the ability of the land to absorb water and replenish aquifers. Over time, these changes can lead to significant declines in water tables, impacting not only the availability of water for consumption, but also the health of surrounding habitats. Climate change compounds these challenges, with shifting precipitation patterns and increased evaporation rates. Regions once reliant on consistent rainfall may experience prolonged droughts, further stressing aquifer levels. The interconnectedness of land use and groundwater systems illustrates the necessity of sustainable practices. Responsible management and conservation efforts are essential in mitigating the adverse effects of these changes, ensuring that aquifers continue to serve as crucial reserves of fresh water for both human and ecological needs. Natural disasters present a duality of resilience and vulnerability within deep aquifers. These subterranean reservoirs, often shielded from surface disruptions, can act as buffers against extreme weather events. Their capacity to store vast volumes of water allows them to sustain ecosystems and human populations during prolonged droughts or erratic rainfall patterns. In periods of severe drought, these aquifers provide a lifeline, releasing water slowly into ecosystems that rely on consistent moisture levels. Despite this resilience, deep aquifers are not impervious to the impacts of natural disasters. Earthquakes, for instance, can fracture surrounding rock formations, potentially altering flow patterns and contaminating these reserves. The structural integrity of the aquifer system can be compromised, leading to challenges in water quality and availability. The hydraulic connections between layers of rock may shift, causing previously stable supplies to become unpredictable. Flooding poses an additional threat, as surface waters can infiltrate these underground systems, introducing pollutants and pathogens. The delicate balance between recharge and extraction is often disrupted during such events. leading to long-term consequences for both water quality and quantity. This intricate relationship underscores the need for monitoring and research to enhance understanding of aquifer dynamics, ensuring these vital resources remain intact and functional even in the face of nature's unpredictability. A sustainable water management for aquifers necessitates a multifaceted approach that prioritizes conservation and efficiency. This strategy seeks to balance human needs with the natural processes that govern these underground reservoirs. Groundwater extraction must be conducted with care, ensuring that withdrawal rates do not exceed replenishment. This delicate equilibrium supports the longevity of aquifers, allowing them to continue providing water to ecosystems and communities alike. Monitoring techniques such as remote sensing and hydrological modeling play a crucial role in assessing aquifer health. These tools facilitate the collection of data regarding water levels, flow rates, and quality, informing management decisions. Understanding the interplay between surface water and groundwater is essential for maintaining the integrity of both resources. Rainfall patterns and land use changes can significantly impact aquifer recharge rates, necessitating adaptive strategies that respond to shifting environmental conditions. Community engagement becomes indispensable in sustainable practices. Educating individuals about the importance of conserving water and the impacts of over-extraction fosters a culture of stewardship. Implementing regulations that promote responsible use, alongside incentives for water-saving technologies, can enhance collective efforts toward sustainability. The integration of scientific research with local knowledge ensures that management practices are both effective and culturally appropriate. This holistic perspective is vital for safeguarding aquifers, which serve as a lifeline for many in an uncertain future. Educational initiatives play a crucial role in raising awareness about deep aquifers. These programs aim to inform communities about the significance of these hidden reservoirs and the essential services they provide. Workshops and seminars engage participants in discussions regarding water conservation and sustainable practices. Visual aids, such as diagrams and interactive models, illustrate the complex geology and hydrology of these subterranean systems. This approach fosters a deeper understanding of the relationships between human activity and aquifer health. Emphasis is placed on how pollution, over-extraction, and climate change threaten these critical resources. Collaborations with schools enhance outreach, introducing students to the fundamentals of groundwater science. Such initiatives encourage the next generation to value and protect these vital ecosystems. Field trips to local water bodies and aquifer sites provide hands-on experience, linking theoretical knowledge to real-world applications. Community involvement is encouraged through citizen science projects, where individuals can monitor water quality and report changes. These efforts create a sense of stewardship and responsibility toward local water resources. Public campaigns utilizing social media and local events further amplify awareness, disseminating information widely and engaging diverse audiences. By nurturing this collective consciousness, educational initiatives contribute significantly to the preservation and sustainable management of deep aquifers for future generations. Research continues to uncover the complexities surrounding deep aquifers, yet many questions persist. The precise nature of their interactions with surrounding geological formations remains elusive. Understanding how these vast reservoirs influence surface ecosystems is crucial. Groundwater flow, often described as sluggish, can affect surface water availability, impacting both flora and fauna. The chemical composition of deep aquifers presents additional challenges. Variations in mineral content can alter water quality, raising concerns about potability and ecosystem health. Investigating these chemical processes not only aids in resource management, but also reveals the intricate biogeochemical cycles that sustain life. Phorographic connectivity among aquifers also remains an area of exploration, with implications for both freshwater supply and contamination risk. Tracing the pathways of groundwater movement sheds light on how pollutants can traverse subterranean landscapes, complicating efforts to protect these precious resources. The role of climate change in altering the dynamics of deep aquifers is an emerging frontier. Predictions about shifting precipitation patterns and increased evaporation rates invoke concerns about future water availability. By examining historical data alongside current trends, scientists strive to anticipate the potential impacts on aquifer recharge rates. Uncovering these unanswered questions will not only enhance understanding but also inform strategies for sustainable management of deep aquifers, ensuring their viability for generations to come. Citizen science initiatives have emerged as pivotal contributors to aquifer stewardship. Local communities engage in data collection, monitoring water quality, and reporting changes that may occur within their regions. This grassroots involvement fosters a sense of ownership and responsibility, ensuring that aquifers are not merely resources but vital components of local ecosystems. In this context, individuals wield tools such as water testing kits, which enable them to measure parameters like pH levels and contaminant concentrations. These observations provide invaluable data sets that enhance scientific understanding of aquifer conditions. Collaboration between researchers and citizens enhances the breadth of knowledge, as traditional methods may overlook localized phenomena. Educational programs designed to raise awareness about the significance of aquifers encourage proactive engagement. Workshops and community forums facilitate the exchange of information, empowering individuals to advocate for sustainable practices. By bridging the gap between science and the community, this approach cultivates stewardship beyond simple observation. Through shared responsibility, communities can develop adaptive management strategies that reflect both scientific insights and local needs. Such measures may include conservation efforts, responsible land use practices, and policy advocacy aimed at protecting these vital water sources. The integration of citizen science into aquifer management not only enriches the data landscape, but also nurtures a collective commitment to preserving water resources for future generations. Transboundary aquifers present a complex web of challenges and opportunities for cooperation among nations. These vast underground reservoirs often extend across political boundaries, complicating management efforts. The shared nature of these resources necessitates collaborative frameworks for sustainable extraction and protection. Differences in legal systems, economic incentives, and cultural values can impede progress, leading to potential conflicts over water rights and usage. Countries that share these aquifers must engage in dialogue to establish joint management strategies. This cooperation is essential for monitoring water quality and quantity, as well as addressing contamination issues that can arise from agricultural practices or industrial activities. Scientific collaboration plays a pivotal role, with cross-border research initiatives aiding in the understanding of aquifer dynamics and replenishment rates. Operators such as the establishment of transboundary agreements can promote equitable sharing of resources. These agreements encourage data sharing and joint assessments, fostering trust and transparency among stakeholders. Engaging local communities in these initiatives further enhances the effectiveness of management strategies. Education and awareness-raising efforts can empower individuals to participate actively in conservation practices. As nations navigate the complexities of shared aquifers, the potential for sustainable water management increases. Collaborative approaches not only mitigate conflicts, but also ensure that these vital resources remain accessible for generations to come. Deforestation significantly disrupts the natural processes that facilitate aquifer recharge. The removal of trees and vegetation alters the landscape, leading to reduced soil stability and increased erosion. This region, once rich with flora, now exhibits a striking vulnerability to rainfall patterns. Without the canopy to intercept precipitation, rainwater becomes less effectively captured, resulting in rapid runoff rather than gradual infiltration. The consequences extend beyond immediate water availability. The loss of plant life diminishes the soil's ability to retain moisture, which further exacerbates the decline of local aquifers. These underground reservoirs rely on a delicate balance of infiltration and retention, both of which are compromised by extensive land clearing. The degradation of ecosystems leads to diminished biodiversity, impacting the resilience of these environments. Hydrological cycles are disrupted, leading to altered local climates. The absence of transpiration, the process by which moisture is released into the atmosphere, creates a feedback loop, further decreasing precipitation in affected areas. Such changes can lead to long-term drought conditions, directly impacting agricultural practices and water supply. This gradual degradation highlights the interconnectedness of terrestrial health and aquifer sustainability. In regions where deforestation is rampant, the struggle for clean water intensifies, underscoring the urgent need for sustainable land management practices that prioritize both ecological health and resource conservation. Restoration efforts have increasingly focused on aquifer recharge techniques that facilitate the natural replenishment of water reserves. One prominent method involves the strategic use of surface water management systems, such as rainwater harvesting, which captures precipitation and directs it into recharge pits or infiltration basins. This approach has shown promising results in arid regions where water scarcity is prevalent. In regions like the southwestern United States, community-driven initiatives have successfully revived depleted aquifers through collaborative efforts between local governments, agricultural stakeholders, and environmental organizations. By implementing sustainable irrigation practices, these projects have not only improved water availability, but have also fostered biodiversity in surrounding ecosystems. In parts of India, the construction of check dams has proven effective in slowing runoff and increasing groundwater levels. These structures create temporary reservoirs that encourage percolation, allowing water to seep into the soil and replenish aquifers. Success stories from these areas illustrate the potential for local innovation to address larger environmental challenges. Integrated water resource management combines traditional knowledge with modern techniques, creating a holistic approach to aquifer restoration. Such initiatives promote resilience against climate variability while enhancing the overall health of ecosystems. With continued research and investment, these strategies may serve as a blueprint for sustainable water management globally, ensuring future generations can access vital resources. Aquifers serve a vital role in maintaining biodiversity and supporting ecosystem health. These subterranean reservoirs not only store water, but also regulate its flow to surface ecosystems, thereby sustaining various forms of life. The presence of aquifers ensures the continuous supply of water to springs, wetlands, and rivers, which are essential habitats for countless species. Maintaining the hydrological balance fosters rich biodiversity, enabling flora and fauna to thrive in these interconnected environments. These formations contribute significantly to the resilience of ecosystems. By releasing water during dry periods, they provide critical hydration to plants and animals, creating a stable environment that supports ecological dynamics. The interaction between surface water and groundwater sustains the intricate food webs that characterize many ecosystems. Aquifers also filter pollutants and sediments, enhancing water quality before it reaches surface bodies. This natural purification process supports the health of aquatic habitats, where species reproduce and thrive. Dhuri Manhals, regions where aquifers are depleted or contaminated, the consequences can be severe. Declining water levels can lead to habitat loss, decreased plant growth, and the migration or extinction of sensitive species. Protecting these reservoirs, therefore, becomes essential not only for human needs, but for preserving the delicate balance of ecosystems that rely on their hidden depths. Understanding their significance can drive efforts to safeguard these crucial resources for future generations. Interactions between these hidden reservoirs and surface ecosystems reveal intricate connections that sustain life. Groundwater originating from aquifers feeds rivers, lakes, and wetlands, creating vital habitats for diverse species. This relationship is essential for maintaining ecological balance, as surface ecosystems depend on the constant flow of freshwater. Nutrient-rich water from aquifers seeps into the surface, enriching soils and supporting vegetation. Roots extend deep into the ground, tapping into these reserves, which can provide sustenance even during periods of drought. The health of agricultural systems is directly linked to the availability of groundwater, influencing crop yields and food security. In arid regions where surface water can be scarce, the role of aquifers becomes even more pronounced. They serve as lifelines for both ecosystems and human communities, enabling survival in challenging climates. The delicate equilibrium is often disrupted by over-extraction and pollution, leading to a cascading effect on local flora and fauna. Aquifer depletion can result in declining water quality, altering the composition of surface water, and affecting biodiversity. The intricate web of life that relies on these interactions demonstrates the importance of preserving groundwater systems. Protecting aquifers ensures the resilience of ecosystems, fostering a symbiotic relationship that has existed for millennia. The future of both underground and surface environments hinges on this understanding. Resource extraction from deep earth aquifers requires careful ethical considerations. The delicate balance between human needs and environmental preservation presents a complex challenge. These underground reservoirs, often untouched for millennia, hold vast quantities of water, essential for agriculture, urban development, and industry. Extracting water from such depths involves not only the immediate impacts on water availability, but also potential long-term consequences for local ecosystems. Communities relying on these aquifers face the risk of depletion, leading to adverse effects on their livelihoods and health. The decisions made today regarding exploitation will reverberate through generations. Striking a balance between economic growth and sustainability becomes imperative for policymakers and stakeholders. Transparency in decision-making processes fosters trust among affected populations, ensuring that ethical considerations are at the forefront of any extraction initiatives. Understanding the interconnectedness of these aquifers with surface water systems and regional climates is crucial. Over-extraction may alter hydrological cycles, impacting not only the immediate area, but also distant ecosystems. Ongoing research is essential to assess the implications of aquifer depletion on biodiversity and climate resilience. Integrating scientific insights with ethical frameworks will guide responsible management of these vital resources, safeguarding them for future generations while meeting current demands. This holistic approach emphasizes the importance of stewardship in the face of growing pressures on Earth's hidden water reserves. Deep aquifers play a critical role in climate resilience strategies, offering a vital resource as global temperatures rise and precipitation patterns shift. These vast underground reservoirs store freshwater that can be tapped during periods of drought, providing a buffer against the increasing unpredictability of weather events. By understanding their locations and capacities, communities can develop sustainable management practices that ensure access to this essential resource. Rakol's research indicates that these aquifers can enhance agricultural productivity, particularly in arid regions. Irrigation sourced from deep aquifers supports crop growth when surface water becomes scarce, enabling food security amidst changing climatic conditions. This reliance on underground reserves also reduces the stress on surface water bodies, allowing ecosystems to maintain their health and biodiversity. Monitoring the extraction rates and recharge processes of these aquifers is essential for maintaining their longevity. Over-extraction can lead to significant consequences, including land subsidence and diminished water quality. Implementing integrated water resource management can mitigate these risks, balancing the needs of human consumption with environmental preservation. In addition, the data gathered from studying these deep reservoirs can inform broader climate adaptation strategies. Understanding the interconnections between groundwater and surface water systems reveals insights into regional hydrology. The future of deep earth aquifer research holds significant promise for advancing our comprehension of subsurface hydrology. Innovative methodologies are emerging, combining geophysical imaging techniques with advanced modeling to explore the intricate networks that lie beneath the surface. These techniques assess the geological formations that encapsulate vast reservoirs of water, often located miles below the Earth's crust. The implications of this research extend far beyond academic interest. They inform water resource management, particularly in arid regions where surface water is scarce. Investigating these hidden aquifers enables scientists to gauge the capacity and sustainability of crucial water supplies. Additionally, the impact of climate change on these systems cannot be overlooked. Variability in precipitation patterns and increased evaporation rates challenge existing water resource paradigms. Monitoring deep aquifers provides a buffer against these fluctuations, ensuring a more resilient water supply. Collaborative efforts among geologists, hydrologists, and environmental scientists are fostering a multidisciplinary approach that enhances the understanding of deep Earth systems. The integration of satellite data with ground-based observations allows for a more comprehensive view of how these aquifers interact with other hydrogeological features. And continued exploration of these subterranean oceans will yield essential insights, guiding policy decisions and resource management strategies for generations to come. Groundwater management policies must prioritize the protection and sustainability of these vast aquifers. Monitoring systems should be established to assess water quality and quantity, ensuring that any extraction remains within sustainable limits. This approach requires collaboration among governments, scientists, and local communities, fostering an understanding of the delicate balance that exists within these underground reservoirs. Regulations must be developed to mitigate pollution from agricultural runoff and industrial activities, safeguarding the purity of the water contained in these aquifers. Establishing buffer zones around recharge areas can significantly enhance protection, allowing natural filtration processes to occur unobstructed. Education programs aimed at promoting conservation practices among water users are essential. Increased awareness can lead to more responsible water usage behaviors. Investment in research and technology is crucial for advancing understanding of groundwater systems. Innovative methods, such as remote sensing and advanced hydrological modeling, can provide deeper insights into aquifer dynamics. These tools will aid in predicting changes and identifying potential risks related to climate variations. International cooperation is also vital for managing transboundary aquifers. As water does not adhere to political boundaries, agreements must be crafted to ensure that shared resources are utilized equitably and sustainably. Such collective efforts can secure the future of these hidden oceans, ensuring they continue to provide vital resources for humanity. Successful aquifer management practices serve as beacons of hope in the quest to harness these hidden oceans. One notable case is the Great Artesian Basin in Australia, where innovative strategies have led to sustainable water use through the implementation of efficient irrigation techniques and the establishment of protective legislation. This vast reservoir has been preserved, allowing agricultural regions to thrive while minimizing depletion. In California, the Sustainable Groundwater Management Act has initiated a collaborative approach among local agencies by focusing on groundwater recharge and the recovery of over-extracted aquifers. Stakeholders are working diligently to restore balance. The integration of advanced monitoring systems provides real-time data, enabling informed decisions regarding water allocation. In the Middle East, the management of aquifers has taken on a unique form in locations such as the Al-Azraq Basin in Jordan. Rainwater harvesting techniques have been employed to replenish underground stores. The construction of check dams and the promotion of sustainable farming practices have contributed to the resilience of this vital resource. These examples illustrate that with careful planning and cooperative efforts, the preservation of deep earth aquifers is achievable. Each initiative reflects a commitment to stewardship, ensuring that these vast reservoirs continue to support both ecosystems and human populations in a world increasingly challenged by water scarcity. Halogulthon's creation among nations is essential for the effective management of deep earth aquifers. International organizations play a pivotal role in guiding policy frameworks and facilitating dialogues that transcend borders. These entities provide platforms for knowledge sharing, enabling countries to exchange best practices and innovative solutions tailored to their unique hydrogeological contexts. Through research initiatives, these organizations conduct comprehensive assessments of aquifer systems, identifying critical areas and potential vulnerabilities. They offer technical assistance and training programs to enhance local capacity, empowering nations to implement sustainable management strategies. Monitoring and evaluating groundwater resources becomes a shared responsibility, fostering a cooperative spirit that is crucial in addressing transboundary aquifer challenges. The establishment of legal instruments and guidelines by international bodies ensures that equitable access to these vital resources is upheld. Agreements promote joint management efforts, recognizing the interconnectedness of groundwater systems. As water scarcity intensifies, such frameworks become increasingly vital in mitigating conflicts and fostering peaceful coexistence among neighboring states. Efforts to raise public awareness about the importance of aquifer protection are also central to their mission. Educational campaigns, community involvement, and stakeholder engagement serve to underscore the value of these hidden oceans. Collective action, guided by international cooperation, represents a promising path towards safeguarding groundwater resources for current and future generations. Effective aquifer management influences various socioeconomic factors that extend beyond mere resource availability. Access to clean water from these subterranean reserves can enhance public health, reducing waterborne diseases that often plague communities reliant on contaminated sources. This improvement in health outcomes fosters greater productivity, allowing populations to engage more fully in economic activities. The agricultural sector benefits significantly from sustainable aquifer practices. Irrigation, supported by aquifer water, leads to enhanced crop yields, which can stabilize food supplies and bolster local economies. In regions where drought is prevalent, these hidden reserves become critical lifelines, enabling farmers to maintain livelihoods. Despite fluctuating climate conditions, investment in aquifer management can also stimulate job creation. Specialists in hydrology, environmental science, and resource management are essential for developing infrastructure that monitors and protects these vital systems. Such initiatives can generate employment opportunities, invigorating local economies while ensuring the long-term viability of water supplies. In urban areas, efficient aquifer management translates into sustainable development. It supports infrastructure planning, informing policies that prioritize water conservation and equitable distribution. This strategic approach allows cities to accommodate growing populations while preserving essential resources for future use. As awareness of aquifer significance increases, community engagement becomes essential in stewardship efforts. Local populations, equipped with knowledge and resources, can actively participate in protecting these hidden oceans. Groundwater modeling serves as a crucial tool for assessing aquifers, revealing the intricate dynamics of these subterranean water sources. These models simulate the movement and characteristics of water within the geological formations, taking into account various factors such as porosity, permeability, and recharge rates. Complex geological structures often present challenges, as they can create variations in water flow and storage capacity. Environmental conditions play a significant role in influencing groundwater behavior. Variability in rainfall patterns, temperature fluctuations, and land use changes necessitate continuous updates to the models. The interactions between surface water and groundwater also require careful examination, as they can significantly impact overall water availability in a region. Technical advancements in remote sensing and data collection enhance the precision of groundwater modeling. These innovations allow for the integration of diverse datasets, enabling a more comprehensive understanding of aquifer systems. Calibration and validation of models against observed data ensure their reliability, fostering confidence in the predictions they yield. Stakeholders have more to say, including policymakers and conservationists, rely on these models to make informed decisions regarding water management. The sustainable use of groundwater resources hinges on accurate assessments, underscoring the importance of ongoing research and collaboration in this field. Understanding the complexities of groundwater systems is essential for safeguarding these hidden reservoirs for future generations. And public engagement in aquifer issues fosters a collective awareness that is vital for sustainable management. Communities residing above these hidden reservoirs play a crucial role in recognizing their significance. It is within local contexts that the implications of groundwater depletion and contamination become apparent. Engaging the public creates a platform for knowledge exchange, where individuals can understand the delicate balance between usage and conservation. Aviti Jain Shive serve to illuminate the intricate relationship between surface activities and subterranean water quality. Workshops and informational sessions can help demystify the science behind aquifers, making it accessible to all. Such interactions encourage citizens to actively participate in monitoring and protecting their water resources. Advocacy groups often emerge from these discussions, uniting individuals who share a common interest in preserving groundwater supplies. They can influence policy decisions, urging local governments to consider stricter regulations on water extraction and land use practices that threaten aquifers. Transparency in water management fosters trust between authorities and the public, creating a shared responsibility for stewardship. This region's future water security hinges on the collaborative efforts of scientists, policymakers, and community members. A well-informed populace can champion initiatives that prioritize aquifer health, ensuring that these vital resources remain viable for generations to come. Industrialization has exerted profound pressure on these hidden reservoirs. Extraction techniques, aimed at meeting the demands of growing populations and economies, often disturb delicate ecosystems. Water tables in certain regions have begun to decline, a direct consequence of increased pumping rates. This depletion leads to a reduced supply of fresh water for both human consumption and agricultural use. The introduction of contaminants into groundwater systems poses another significant concern. Chemicals used in various industrial processes can seep into aquifers, altering the composition of water and threatening the health of entire communities. Heavy metals, nitrates, and volatile organic compounds have been detected in some areas, raising alarms about potable water safety. Monitoring efforts have become essential in assessing the integrity of these resources. Advanced technologies, including remote sensing and geochemical analysis, enable scientists to detect changes in aquifer conditions over time. This ongoing surveillance allows for informed decision-making regarding resource management. In addition to direct contamination, land use changes associated with industrial activities can exacerbate runoff issues. Urbanization increases impermeable surfaces, leading to decreased natural recharge rates. As a result, the capacity of aquifers to replenish diminishes, further stressing these critical water sources. Preserving these deep aquifers requires a multifaceted approach, engaging stakeholders to balance industrial growth with sustainable practices. Integrating aquifers into urban planning emerges as a vital strategy for ensuring sustainable water supply in the face of increasing demand. Urban environments, characterized by their dense populations and infrastructural complexity, often overlook these hidden reservoirs beneath their surfaces. This oversight can lead to over-extraction and degradation of vital water resources. Incorporating aquifer management into city planning entails recognizing the intricate connections between surface water systems and these concealed sources. Effective monitoring and data sharing among urban planners, hydrologists, and environmentalists are crucial. Advanced modeling techniques can predict how urban development affects groundwater levels, allowing for more informed decision-making. Rainwater harvesting and permeable surfaces can enhance aquifer recharge, creating a symbiotic relationship between urban infrastructure and groundwater sustainability. Such practices bolster the resilience of water supplies, particularly in regions experiencing prolonged droughts. Legislation supporting aquifer protection zones can safeguard these resources against contamination and excessive depletion. Public awareness campaigns can foster a culture of conservation, encouraging communities to participate in preserving their water sources. Through coordinated efforts, urban planners can facilitate a future where aquifers play a prominent role in securing water supply. This approach not only addresses immediate needs, but also prioritizes long-term viability, ensuring that future generations inherit a stable and sustainable water system. Emerging contaminants present a growing concern within deep aquifers. These substances, often originating from industrial processes, agricultural runoff, and urban activities, infiltrate subterranean water sources, raising questions about their long-term impacts on both ecosystems and human health. Detection methods have evolved, allowing scientists to identify trace amounts of pharmaceuticals, personal care products, and various chemicals within these deep reservoirs. The depth and isolation of these aquifers do not guarantee immunity from such pollutants. Over time, contaminants can migrate through geological formations, undermining the purity of previously pristine water supplies. Studies indicate that certain emerging contaminants can persist in geological formations for extended periods. increasing the likelihood of their eventual entry into the human water supply. This phenomenon is not limited to specific regions. Diverse geological settings across the globe experience similar infiltration. Monitoring networks are essential for tracking these substances and understanding their distribution within aquifers. Research highlights the importance of developing effective filtration and remediation techniques to address these pollutants before they reach the surface. Collaborative efforts among scientists, policymakers, and industry stakeholders are vital in crafting protective regulations and innovative technologies. Ensuring the integrity of deep aquifers requires a commitment to ongoing research and resource management, recognizing that the preservation of these hidden reservoirs is critical to sustaining life above ground. Climate mitigation strategies increasingly acknowledge the significant role of deep earth aquifers in stabilizing ecosystems. These subterranean reservoirs hold vast quantities of freshwater, which can be crucial during periods of drought, enhancing resilience against climate variability. Their ability to store and regulate water plays a vital part in sustaining agricultural productivity, ensuring that crops receive the necessary hydration even when surface water supplies dwindle. The interconnectedness of aquifers with surface water systems creates a buffer, allowing for the recharge of rivers and lakes, especially during times of high precipitation. This interplay helps maintain local biodiversity, supporting various species that rely on consistent water availability. The gradual release of stored water from these depths can also mitigate flooding, as it reduces the immediate impact of extreme rainfall events. Carbon sequestration is another aspect where deep aquifers contribute to climate strategies. Certain formations can capture and store carbon dioxide, preventing it from entering the atmosphere. This geological feature offers a dual benefit, reducing greenhouse gas concentrations while simultaneously safeguarding water supplies. Research into innovative extraction techniques and sustainable management practices is essential for maximizing the benefits derived from these aquifers. Their preservation not only serves the immediate needs of human populations, but also plays a broader role in achieving long-term environmental stability. If interdependencies between aquifers and global water security are intricate and profound, these vast underground reservoirs act as a critical buffer against the variability of surface water supplies. In regions characterized by erratic rainfall patterns, it is the aquifers that sustain agriculture and drinking water needs, ensuring resilience in the face of climate change. The delicate balance maintained within these systems is essential for supporting ecosystems that rely on consistent hydrological inputs. The connection between aquifers and surface water bodies is evident through the process of natural filtration. Water seeping through soil layers replenishes these subterranean stores while purifying it simultaneously. This synergy is vital for maintaining the quality of water that eventually emerges in springs and rivers. The health of aquatic habitats often hinges on the stability of these hidden reservoirs, illustrating their role as lifelines for both terrestrial and aquatic organisms. The depletion of aquifers poses a significant threat to global water security. Over-extraction can lead to land subsidence and reduced water quality, creating a cycle of scarcity that impacts both human and ecological communities. Sustainable management practices are paramount, ensuring that these vital resources are used judiciously. The intricate interplay between groundwater and surface resources underscores the necessity for comprehensive strategies that safeguard these essential components of our planet's hydrological framework. Global awareness surrounding deep earth aquifers is paramount for sustaining this vital resource. Their vast volumes of water, often hidden beneath layers of rock, represent an invaluable asset for both current and future generations. This region beneath the surface is not merely an abstract concept. It plays a critical role in the overall health of ecosystems and communities, influencing agricultural practices and drinking water supplies. Challenges faced include over-extraction, contamination, and climate change, which all threaten the delicate balance of these subterranean reservoirs. Urgent action is required to ensure these aquifers are managed responsibly. Sustainable practices must be employed to monitor their health and replenish their reserves, thus ensuring they can continue to fulfill their roles within the hydrological cycle. International cooperation is essential, as many aquifers span national borders. Collaborative efforts can help establish regulations and frameworks that promote the equitable and sustainable use of these resources. Education and awareness initiatives can empower communities to understand the significance of deep earth aquifers and their role in global water security. Investments in research and technology will further enhance our knowledge of these systems, allowing for more effective management strategies. Protecting these hidden oceans is not just a local concern. It is a global imperative that requires collective action to preserve this critical resource for the future.